Okay, I'll probably start now. So first thing is I'm going to try to go through the week 10 tutorial. Although I provide answer, but I still think probably the solution is quite a lot of like content in there. I just quickly go through, and particularly if you have any question that the solution confuse you, I wanted to answer those questions. So let me share my screen. Week 10 solution. So I can do some handwriting and help you go through all this. So the first question, anybody have a question about this or feel this is hard to do, or any feedback from this question? Is that nobody? Is that too easy, or what do you think about this one?
Yeah, I think.
Well, it's not hard, but it's just too tedious in calculating the final results.
Yeah, so like if in the exam I ask you to do this, I probably just ask you to do it in one way, not all different methods.
I mean, the first three questions, sub questions, they're okay, but the last one is it just takes too long to get the final result.
Okay. The zero pole matching, right? That's okay. Let me show you. So this is the formula we use to do the first three methods: forward difference, backward difference, and also trapezoidal. So we just use this first left half and replace what is in here. Say if the GS is 1 over S, just use those things to replace it. For example, the trapezoid, we just use S. So S equal to 2 over T. Then put it in to do the calculation, right? So there's no challenge for this. Then we can get our representation in transfer function equal to something like that, right? Then from here, so this is actually, I'll put in there. So it's the Z transfer function or pulse transfer function. From here, you can get what is UK equal to UK minus 1 plus 0.25 EK plus EK minus 1. So no problem with all this, right? That's straightforward. Involve two steps. First step is to replace S with Z. So in three different methods, basically just this representation is slightly different. Then you get the Z transfer function. That's the first step. And the second step is with Z, you kind of move the UK one step forward. If it's Z minus 1, you got step back. So got familiar with from the Z transfer function to this is the time domain. And this is what computer used to do the calculation, okay? If you design a controller, this is your controller. Your controller will take the reading from the current reading and the previous reading and also based on your previous output to generate a new controller signal. So that's the first one. So zero pole matching. So the problem with this thing is in a general case, it's easy. However, normally what I give to you is, oh, not this one. In the general case, it's easy, but what we give you is, where's the, page 57. However, the challenge part is this bit, the step 4. How do we actually matching the games? So there's 3 different situations. Let's go through the steps. So the first thing is you have to get all your poles and zeros. Sometimes zeros is less than the poles, and you have to match with 0 at infinity. So you always have same number of poles and zeros. And each one of these poles and zeros, you get this kind of relationship. If it's a real pole, you got z equal to e negative at. If it's a complex pole, you got this representation. Then if it's infinity, you got z equal to -1. So you follow these steps. And the next thing is when you have a discrete time system and a continuous time system, you have to make sure they have a same gain. Normally at DC, so at when s equal to 0. Okay? So normally you match the gain of the ds with dz when s equal to 0. However, sometimes, so that's the first thing, right? You s equal to 0, you got z equal to 1. So you make sure they have the same gain. However, sometimes you have s equal to 0, you got your gain is 0. In that case, you divide this ds with s. So you not look at the gain at DC. Instead of you look at the change of the gain at DC. So it's kind of you take a derivative of your DC of your continuous system, and equivalent for the continuous system divided by s. For discrete system, it becomes divided by z minus 1. Okay, because s equal to z minus 1, right? That's how we well, s equal to 0 corresponding to z equal to 1. So basically, s equal to 0, you get z minus 1 to divide it. So you cancel out a 0. So you're not matching the gain anymore. You're matching the change of the gain. Okay, so that's one case. When that's the second case when ds equal to 0. Then third case is when ds equal to infinity. Then in that case, you can't compare the gain because both continuous and discrete time goes to infinity. So in that case, you have to choose another frequency of your interest. So normally this is where you have your bandwidth. Omega 1 is somewhere around your cutoff frequency. That's where the most of the system is running at. And you make sure at that frequency, you have the same gain. And that's the case, I think, in our question, right? In this question. Not this one. Is that this one? Let me see. No, not this one. That's the question 2. We'll have that case. But look at this 0 pole matching. Let me walk through. I can't really exactly remember what will happen for this. So this is fourth one. 0 pole matching. So we got our poles at 0. So that because this is a transfer function. So pole is s equal to 0. And you got this is corresponding to z equal to est, which is equal to E0t is equal to 1. Then 0, you got s equal to infinity because you don't have any 0 here, right? If actually there's 0, but it's s minus infinity. So it just you become just a constant there. So in that case, you get z equal to -1. Okay, that's just set up. Okay, so with that, we can get our gz is equal to, well, ideally it's just on the top is z plus 1, at the bottom is z minus 1. However, we wanted to multiply with a k, or put a k in the front. This k is to make sure the gs is equal to gz. So normally when this is s equal to 0, this is z equal to 1. Okay, so you want to make sure this happens. So what we do is we go do the calculation. Let me see. So to calculate the GS, let me have a look. Well, this is case 3 in the lecture slides. So you identified. This is when we have ds equal to infinity, because when we look at this, the gs equal to 1 over s. When s equal to 0, this goes infinity. So it's case 3. Okay, so you have to really make this k to be something in a different frequency. Okay, so we choose a certain omega. Say we just say omega equal to 1. This is where we wanted to have these two equal. So you can't take s equal to 0. So s equal to j omega, which this becomes omega equal to 1. So s equal to j, basically. And we want to match the gain between these two. So in this case here, gs, when s equal to j omega, becomes 1 over, well, omega is equal to 1 here. 1 over j equal to 1. So that's what we mean. We want to have our gz equal to k multiply with, so here z is equal to e, est. S is j omega, so omega equal to 1. J omega equal to 1. T is equal to 0.5, is it? So it's j 0.5. And this is a plus 1, and the bottom at e j 0.5 minus 1. Okay, so basically this is a complex number. We want to find its value. This is when say z equal to e s t and e s equal to j, t is 0.5. So z is equal to this. Okay, we'll put that in there. And this is equal to 1, because this two needs to be kind of equal to each other. So pretty much what we need to do is, what is this? Okay, so it becomes just mathematics. How do we calculate the magnitude of imaginary number? So if you get a computer, you put this in MATLAB and it gives you like that. If you don't, then it becomes, this becomes well, mathematically, let's just look at this thing. So we know that Euler's formula is Ex equal to cosine x plus j sine x, or Ej. x. That's Euler's formula. And then this is becomes the top is cosine 0.5 plus sine j sine 0.5 plus 1. On the bottom is cosine 0.5 minus plus j sine 0.5 minus 1. So you just calculate the magnitude of this number. So the real part is this and this, that's the real part. This and this, that's the real part. This is imaginary part. So you calculate how big is this, calculate how big is this, and you divide. And ends up to be, this whole thing is equal to 4. Okay, do you understand all this? Hello?
Yeah, I think so.
You understand all this? Okay, that's good. So this part, why I ask you to do all this is because all these mathematics, although when we actually do the question or we have a computer, we don't need to go through this, but you doing this manually help you to understand like where all this come from. Otherwise, you only know to kind of just click the button, run the MATLAB program without understanding like mathematically what's happening. And also for the question 3 and 4, that's exactly what I'm trying to do. So look like I haven't taught anything about this in the lecture, but I still want you to practice a little bit on question 3 and 4. So this question 2, it's the zero pole mapping, but this is actually the case. I think it's the case. Why it's always coming to this thing? It's the case 2. You got this case 2 for the question 2. Okay, so you guys understand this, so I'm not going to go through this. If you know how to do it, it is tedious, I accept, but this is just trying to help you kind of understand a bit more, like how mathematically this is kind of evolving. Otherwise, if you just know the MATLAB can do this, then you don't really understand what's going on. So question 2, do I need to go through it or not?
Sorry, you just say which row, A, B, C, which row we were going to apply for these questions? Like,
so this is question 1 is case 3. Question 2 is case 2. So this is when you have a gain equal to 0, I think, because you have a 0 at the top, right? When s equal to 0, you got this equal to 0. And this case 1 is when s equal to 0, this goes to infinity. So this is case 3. This is when you got case 2. If you look at this, right? 3 cases, A, B, C.
yeah.
The question 1 is this last case. And this question 2 is this case B.
Okay.
So you have to use this bit to match the gain. And generally you got this simplest case. So just, I don't think it's hard, right? It's just, yeah, it's tedious.
I think I've tried to figure out some like result of this from this question, but I'm not sure why. Like my mark is 70 out of 100. I'm not really sure. Like
okay, mostly because you didn't do the question 3 and 4.
Oh.
Right? Did you do that? You didn't do the question 3 and 4. So I'll go through the question 3 and 4 because this is something I probably haven't taught or covered in the lecture, right? This is what I assume you already learned from previous subject. But however, some of you haven't learned any subjects like in the area, and some of you probably forget about this. So I'll just go through this one. The question 3 is we have a filter. We wanted to do some kind of menu kind of border diagram. Right? So for doing that, say GS equal to AS plus A. Okay? So for doing the Bode diagram, we got S equal to J omega. So J is the symbol of the imaginary number. Omega is the frequency. So this gives us the Bode diagram. So horizontal axis is omega. Vertical axis, you have two things, right? One is the magnitude. The other one is phase. Because it's an imaginary number, you have a vector, like you have the size. This is how large it is, and you also have the phase. All right, so then this becomes A J omega plus A. A is a constant here. I'll just mark it here. Say this is A. Okay. So how do we plot this? See, how do we plot this in here? So if you look at the gain, gain is how big this thing is, right? So let's look at the omega. We're trying to figure out the plot from omega from 0 to infinity. So if we think omega is 0 to start with, this when omega equal to 0, this GS, look at the gain. Is equal to just A over A, right? It's equal to 1. So you got this is equal to 1. So when omega is very small, even this part just compared to A, it's very small. So you ignore that part. So it's pretty much like something like that. Then we say if omega is equal to very large, well, this will end up to be GS is equal to A over infinity, which will become 0. So eventually it goes like very small, right? And we also have look at a particular point, say if omega equal to A, and our GS is equal to A over AJ plus A. Right, so this is equal to 1 over square root of 2. That's it. Right, so somewhere over at this point, you got like 0.7. This is a 0.707 equal to 1 over square root of 2. All right, so if you draw the whole thing, link this together, it looks something like that. So there's a corner cut off. So that's your Bode diagram in the gain frame. This is your gain. And at this corner, you get this drop a little bit. So it's not perfectly like a two straight line.
Professor.
Yeah? Yes?
Isn't the value of magnitude is 0 at omega infinity? So the graph.
Yeah, 0 at infinity.
Yeah, but so the magnitude is like -1 at when omega is infinity from when I see the graph. It should be in the axis, I think. The point.
Over here. Sorry, I didn't get you. Could you see that again?
Like when it's infinity, omega is infinity, the end of the graph should be on the axis, right? On the axis of omega.
Oh, okay, shouldn't go continuous.
Yeah, yeah, that's right. So it's -1. Somewhere between minus.
No, the thing is when we draw this is in log axis. So this is not 1. Normally you get a 20 log of our game.
Okay. Yeah, that
20
makes sense.
log, that makes sense. Okay, let me explain that. I didn't realize that's going to be a problem. So 20 log G. So when you have this 0, log 0 is infinity. Negative infinity, actually. All right? This is going to be 1. Actually, is 20 log 1. This is become 0. You understand? So we draw this thing into a logarithmic axis. That's why it becomes a flat and then goes down. Okay.
No.
Yeah. So this is not a linear. This is not a linear y-axis. It's a logarithmic y-axis. All right. Sorry, I didn't mention that part.
You.
Yeah. So it's logarithmic. Then we look at the phase. What happened to the phase? Again, from omega equal to 0, if you look at this, omega equal to 0, this is 1, and it's only the real part, right? So its phase is 0. Phase is 0 in this case. So when omega to 0, it starts from there. Well, it won't be exactly from 0 because you always have a little bit omega there, right? So it's kind of always like real. Then we look at omega super big, it will become, let's say, the phase is equal to, how do we calculate this phase? Anybody knows how to get the phase of this? Let me do this. A, J, omega plus A. So to do the phase, because the imaginary thing is at the bottom, it's confusing, right? So what do? We multiply the top and the bottom with J omega minus A. All right, so what this gives us is, move this down a little bit. Okay, so what this gives us is the bottom is become, we have J square equal to -1, okay? This is what make the imaginary number. So in here, you got a negative omega square at the bottom, you got a plus AJ omega, negative AJ omega, they cancel out, then minus A square. So the bottom is a imaginary number, and it's actually a negative number. And on the top, you got A, I'll just leave A here. And we'll put this J omega minus A over here. Right, so this is a real number. Well, basically, this is just a negative number, right? So if we look at the phase, what matters is this part. Okay, so the phase of, that thing comes again. So phase of this thing is basically equal to, if you draw a triangle here, this is the other one. You get real part is, because there's a negative over here, so I'll do a conversion. So this is A omega square plus A square. This becomes A minus J omega. Right, so real part is A. Imaginary part is, goes here, negative J omega. So it's point over here. Okay, so the theta is this, which is negative arc tangent omega over A. So this is a general formula. Something is wrong with my stuff. General formula to get the phase, which is okay for now. Right, we can use this to get our phase. So when omega equal to 0, you get our phase is 0. Then I'll just draw more, so negative half pi. So you can see when omega equal to infinity, this thing goes to 90 degrees, but it's negative over here. So it goes to negative 90 degrees in the end. When omega equal to A, this is negative arc tangent 1, which is negative 45 degrees. So this is like when it's equal to A, it's negative 45. So it's something like this. This is messed up. Let me close this down and do it again. Had this problem a few times. So from that, you know, the first order system, the phase goes from 0 to negative 90 degrees if you have a pole, one pole for the first order system. For the second order system, because each pole will move that 90 degrees, so second order system goes from 0 to negative 180. Okay, so that's how the system works. Let me wait until this come up. This Microsoft thing is not very reliable. Okay, it's back here. We still almost got what we want. Just draw a little bit something here. So we've got our phase is something like this. So this A is represented to this A corresponding to negative 45 degrees. And this will be negative 90 degrees for the infinity. Right, so we got a general kind of bow diagram for the first order system. The question is find the cut-off frequency omega p. Okay, so the cutoff frequency for this one is when omega equal to A. So when omega p is equal to A. Okay, so this is also what we did for our anti-aliasing filter. Actually, this is our anti-aliasing filter. So the whole point of this question is just trying to help you understand a bit more when we do design by emulation. Where is this filter come from? Like, why do we choose this filter? Okay, so because its cutoff frequency is A, and it's right at the corner, and you can see these two A's are the same, and the gain of this filter, when it's at low frequency or DC, it's actually equal to 1. This 0 over here in the logarithmics axis is actually 1 in the real term. Manually draw the bow diagram, which we just did. And phase lag at omega p. So what's the phase lag at omega p is 45 degrees. So if you put this in there, this filter in the system, and we look at when omega equal to A, it'll cause 45 degrees phase lag. So this is very likely if you have a system, it's going to become unstable. That's why normally what we design this system, this omega p is equal to 10 times of the bandwidth, right? The sampling period, omega s is 20 to 40 times of the bandwidth. Okay, so our anti-aliased filter is half of that. Right? So that's what we do. The next question is if the bandwidth is only 1/10 of omega p, okay? What's the phase lag is causing? So that's when we have omega is equal to 1/10 of omega P, which is 1/10 of A. What's the phase lag? So we just use the equation is already gone. So equation is equal to arc tangent omega over A. So this will become negative. It's always a phase lag. So arc tangent will become 0.1 because omega is only 1/10 of the A. Okay, so this is negative 5.7 degrees. Does this make sense to you guys? Anybody have questions? I think this is the kind of menu design. If you have a anti-alias filter, how do we choose and what happened? So if the system bandwidth is omega p, we work backwards. We make the omega p 10 times faster. Then we can calculate the phase kind of delay. This is the phase loss due to this filter. You lost like 6 degrees. In the next few minutes, I'm going to explain that how do we do that in MATLAB. But this is like how do you do it in kind of manually. Okay? So this part is which you should have known, but in case you don't, this is the content I'm trying to help you to understand this bit. Does this all make sense or not? No, the response I think is probably you still don't understand this. If that's the case, could you go and look for some border diagram kind of drawing kind of tutorial? I think I put that in the tutorial question, right? There's
yeah, I think the solution is here, but just too simple.
The link is in here. You can kind of manually draw the plot, or you just go Google it. This is just mathematics, very mature mathematics. Okay, so this question is for the purpose when we do design by emulation. How do we got this anti-alias filter? How do we calculate this manually? I think I record all this, so I'll put this on the website. If you don't understand now, you can go have a look afterwards. If you still don't know, probably you can ask me next week. All right. So this question 4. So this is another part of the design by emulation, is when we look at what's the zero or the hold. What's the impact of this thing on the system? Okay, so for this part is actually, we have a formula from the book, because this one is an approximation. It's not 100% accurate one. Let me find the lecture 10. Lecture 10 stuff. Where's the lecture 10? Yeah. Design by emulation. I can't remember which slide we talk about this. This one. Okay, so we have to look at how much impact a zero or the hold has to the continuous time system. And this is a kind of almost equal. So it's estimation. It's not exact number. So you will be off by like 1 degree, half degrees, or something like that. Depends on the sampling period, sampling time. If you have higher sampling time, this error will be smaller. But roughly, you got very close. Right? So the phase lag from the zero or the hold is equal to negative omega t over 2 multiplied with 180 divided by pi, because normally this angle is in radians. So this is omega is in radians. Okay, so omega is is that. That is our horizontal axis. It depends on what frequency we look at. It has different kind of delay. So that's what this question is asking for. How much the phase margin decrease caused by zero overhold when sampling. So different sampling time also will cause the difference. So let's first write down the formula over here. I can't really remember that. Let me write it down. Why it comes there again? This one. So it's -12 omega t. Okay, so back to here. So the formula to do that, the delay, or I would say delta theta equal to -omega t over 2. So why it's over 2? Because it's kind of half step delay. Anybody don't understand where this come from? Do I need to explain why is it half t? Why it's half t? Yes or no? I don't get any feedback, so I don't know what.
Yeah, if possible, please explain more.
Okay, so why is this half t? Because I think there's some. It's not from this lecture. It's week 9. Let me show you where you find this information. Why this thing so slow? Zero order hold. So when we model this, all right, that's where this comes from. So I don't know which slide it is. Let me try to find it. It's from here. Time delay introduced by signal reconstruction. So this is where this zero order hold is. Okay, so exactly this slide 42 in week 9. So originally we have this solid signal if it's continuous. However, what we got is this dot point, right? Because we don't have the signal from the controller. Controller give us these discrete instance. So what we did is from this discrete instance, we do a zero order hold. So we hold the value until we got next value. Okay, so this green one is the output of zero order hold. The solid line is what's supposed to be. The difference between these two, if you do the green and solid line, so green one is zigzag, we can't really see what it is. But the green one can be kind of averaged out with a red dot. Then we compare the red dot and the blue line. So on average, this is kind of delayed by half of this sampling period. So this is where it's come from. You got a delay of half of the sampling period. And this, we make that into the sampling periods t. And at certain frequency, so it becomes omega t divided by 2. And this is where it's come from. So this is where this part, negative omega t divided by 2, that's coming from the delay. This is coming from E negative omega t divided by 2. Okay, this is coming from here. And this multiplied 180 divided by pi, sorry. This pretty much just to convert the unit from radians to degrees. So that's nothing. Right, so that's the reasoning behind that. So then we need to do the calculation. Okay. So firstly, we have to find where this omega is. Okay, omega is what? And we look at this this plan. where is the phase margin? Okay, so we need to know where the bandwidth is, right? So where is omega? This is our bandwidth of this system. Right? So the bandwidth is when a system, you got this Bode diagram, when this omega, you got the gain equal to 1. Okay, so this is when this inside this is the system can handle. This inside is system can handle it. Anything after that, the system will block it. This will be blocked. So on the left will be go through, that's what we call the bandwidth. So this is when the gain of this thing equal to 1. Okay, so we'll go back to find the omega from there. Okay, so this is when we have 5. We don't know the omega yet. So the bottom is S plus 3. Right? So that's where we start, and we normally get S equal to J omega. Right, so putting there, that's 5. So that's x squared plus 3s. So s squared becomes J omega squared plus 3J omega. This is equal to 5. J squared equal to -1. So this is a negative omega squared plus 3J omega. And this needs equal to 1. And we need to find what is omega. Right? Anybody know how to do this? How to know the magnitude of an imaginary number? So if you don't know, you can multiply this to the other side. So basically equal to negative omega squared plus 3 omega j is equal to 5. So what is this? This is imaginary number or complex number. This is the real component. This is imaginary component. So the magnitude
we
of
have
that
to
is
compare with like 5 plus 0 j. So compare imaginary part with imaginary, real part with real. I think so. That's
no,
right.
no,
Okay.
because this is absolute value is the magnitude. So you have to get the magnitude of the bottom and the magnitude of the top. Well, 5 is a real number, so magnitude is 5. So this is an imaginary number. You have to find what's the size of it. And to calculate that, this is the real part square plus imaginary part square. This is equal to 5. Is that how you calculate? So you get A plus B.
Isn't the real part 1 minus omega squared?
There's no 1. This is absolute value. Sorry.
Oh, yeah, yeah. Oh, sorry.
That's absolute value. Okay, so how do you get this? The magnitude of this. This is equal to square root of A squared plus B squared. Right? And the top is just 5. So this bottom thing, change a different color. This needs to be, this whole thing, the value equal to 5. So basically you got this. And if you just say omega squared is something, this is something, or x, and this will become square root of x squared plus 9x equal to 5. So it's a quadratic equation. And we know this x must be positive. So only look at the positive, then omega is positive. So this gives you the solution of omega equal to, I think, 1.5. Does this make sense so far? So this is if you need to kind of find where the cutoff frequency is. So we do all this in MATLAB. If you just draw a Bode diagram, this is all in MATLAB. So I have to go a bit quicker, sorry, because otherwise I don't have time to cover the example anymore. Also, what I'm going to do is you have to go to the other lecture or other tutorial, I'll keep going. I don't want to go too quickly because you miss out. I'll keep going and I'll record all this. If you have to go earlier, that's fine. But I'll keep going in the normal speed so I can cover everything. If you miss out, you can come back and watch the video. Okay, so that's how. Otherwise, I don't have time to go through everything. So this is how we got this omega. This is what we call a cutoff frequency. In MATLAB, you just do a bow diagram. It gives you all these stuff from the plot, which I'm going to go through very quickly. Okay, so you got omega, then the loss of the phase is we come back here, right? We have our omega and we have our t, and we just put in there. So delta theta in the first case is negative omega t over 2 180 over pi. So negative omega here is 1.5 over 2. T here is 0.5 seconds. Then 180 over pi. This gives you negative 21 degrees. So this is again an example I want you to do manually, which I didn't discuss in the lecture. However, this helps you to understand where this delay coming from the zero or the hold, like the things behind the scene. When you actually calculate your calculation, you don't need to do this manually. Okay, so the next step is I'm going to explain how to do the design by emulation using MATLAB. Okay, so the topic covers week 10. So it's from here. These steps. Okay, let's go through one example of these steps. Then you will be quite clear with what's going on, particularly for your project design. Okay, so we have to design the system in continuous time, check the behavior, choosing the sampling frequency, add the sample data system element. Okay, so this part is what happened in here. So these are the two sampling data components to the system. So I just mentioned that if we have to calculate manually, that's how we do it. Now we're going to talk about how to do this in MATLAB. Okay? Then you have to design your control rule and check the performance of your digital controller. Okay, so let's start my MATLAB. I think this one. No. Okay, so I already have some code written here. I'll just run it very slowly. So we have a system, G. So when you design your project, this is your modeling. So you will have something different from me. Okay, so that's up to you. You find a physical model, you come up with a transfer function. That's the start point, right? So this is my example. You have something different. You might have a third order system, or even things more complicated. This is just preparation for the reference input. Okay, so I just get some signals to sending. It's a step response to the signal. So to the system. This command is I construct a feedback system. So at the moment, I don't have any controller. It's just the G and itself. So if I draw the system a bit over here. Say I have GS, which is 1 over 0.2s squared 0.5s plus 1. 0.2s squared plus 0.5s plus 1. So initially, I don't have any control. This is our output. This is supposed to our control signal. Say I don't have any control. Say just this is just put a 1 there, okay? And I got a feedback. So this is no control. We firstly just run that, and I'll just plot the step response. Just have a look at see what it looks like at the beginning. Something's wrong. I didn't run. Sorry, I changed the code a little bit. Just run this again. So that's the step response of our system. Okay, so look at the problem here. We have our reference is equal to 10. Our step response, although it's stable, but it's stable at 5. So it doesn't go to 10. So we have a large steady state error. Okay, so that's the first problem. And also it's quite slow. It takes like 2 or 3 seconds before it goes to stable. If I just write down rise time, it's just say it's quite slow. Rise time is 0.5 seconds ish to get 90%. Its overshoot is about more than 20%. Okay, so the main problem is it's not getting to our reference. So it doesn't go to 10. If you put a command here, if I put a reference input here says 10, and y is actually equal to 5, you don't really follow the reference. So that's the main problem. So we have to get somehow a controller here. We have to get a controller here. And what I do as a design PID control to achieve, so this no longer become 5. I want this to be 10 and with certain kind of overshoot and with certain kind of stability, phase margin. Yeah, so that's kind of the requirement we want. So let's just play around. I delete all this stuff. That's not necessary. Say I've got a KP, KI, KD. And from here, I use the PID command. If you just help PID. So this tells you what this KP, KI, KD is, okay? So if I just do a PID control and want to see what comes up with phase margin, and also what's the kind of the system step response after that. See, at the beginning, I have nothing. Let's do that again. So now I have nothing. So figure 11 will be the same thing as the original system. So this is original system. This is a controller, but everything is like 1 and 0. So I really didn't do anything. And if we look at the margin here, the phase margin, I plot here. Okay, the phase margin is quite good. Actually, you get 100 degrees, so it's very stable. But however, it doesn't go to my desired kind of steady state. So what do? Is I do some try and error. Okay, in reality, you don't just randomly try it. You have to follow certain kind of design rules, which I think last week I put that in the there's Wikipedia about how to design a PID controller. You can follow that. So now I put a gain there, KP, a very large gain. Right? So what this will happen is you can see that's original system. This is our new system. It's much faster, right? Goes up very quickly. However, it gets some stability issue. If we look at the margin, margin only have 8 degrees. Then we look at steady state, you have small arrows here because we want to go to 10 because our reference is 10. It goes to nearly 10. If we, you got steady state. So it's 9.8. It's close. So steady state is good, but it's too much kind of instability. So to do that, KI normally will give us the steady state benefit, make the system steady state, approach to steady state. And KD sometimes will help with the stability. So what we do is say we don't need to have that much gain. Say that's too much. Let's make it slightly smaller. And we put an integration there. And we put a little bit of KD, or like a predictive term there. Let's do that again, design a new system. Right, so this is the new system. You can see again, compared to the original one, it's much faster. That's what we want. And it has overshoot. So overshoot depends on your application. Sometimes you want to go very fast, you get sacrificed by some overshoot. That's okay. In this case, that's what I'm going to do. And you can see the steady state of the system is 10. So there's no arrow because we have this I there. Once you get I there, it's always become there's no steady state arrow because if any arrow there, this component is going to add all those arrows together, even a small arrow, they're going to accumulate to a bigger value and eventually become compensated. So that's what KI is for. So then we look at the phase margin. So phase margin is 26 degrees. Right? So let's say this is what we want for the continuous time design. You can muck around with these parameters, get something different. Okay, it doesn't matter if the controller suits your need, then it's okay. So this is the first and second step. You have your system and you design a controller that suits the continuous performance. Right? So you should start from something like that. You can get a model from examples from other website or other cases, write a story about that. Then design controller. So PID is just one way. You can do other controllers as well. There's no limitation here, but probably you just go with PID because that's what I use as example. If you're probably more familiar with that. So in this case, say this is a good controller, and the phase margin is 26 degrees. I remember that value, 26 degrees of phase margin. You can see it from here. So phase margin, and also the WCP, that's the critical frequency. That's the cross over frequency. So if I draw it from here, so the phase margin and crossover, so that's over here. That's 16.4. So that's roughly, but it's 6.24. That's the crossover frequency. That's when the magnitude equal to 0. Okay, remember this is a logarithmic graph. In here, 0 means 1 in the linear gain. So 1 means this is the boundary. All the signal before this or lower frequency will be magnified. All the signal after this will be reduced. Okay, so this is kind of the band, the system critical crossover frequency the system has, and this frequency will corresponding to the phase margin. So if you look at this, the phase margin, you got 26. That's where it come from. You got over -154, and compared to -180, you got 26 kind of phase margin. Okay, you can look from the board diagram by plot the board diagram just there. And remember, you plot board diagram, you don't plot this system. System is the closed loop. You plot the controller multiply with the plant. Okay, so I'll show you what's the controller look. The prompt is this. That's the original one. The controller is this one. So it's KP, KI, KD with KP, KI, KD, the value you set up over here. So the bold diagram is for open loop. So it's the it's this one. Just C multiplied with G. And the margin, phase margin, is also look at the open loop. Okay, so you got a phase margin, gain margin. So WCP is our cutoff frequency, which is 16, and phase margin is 26. And remember this 26. Now, next step is we have to do the design by emulation. So this is our controller, perfect controller. We wanted to have this. However, we wanted to have this in our computer. So how do we get a computer digital controller to do exactly that? So firstly, we have to select our sampling frequency. So I do another board diagram. So remember, this board diagram is for the system. That's for the closed loop. Okay, you have the feedback. Yeah. So this is the system is feedback. If I plot this, so if I just compare, this is open loop board diagram. This is a closed loop board diagram. Okay. This is for the analyze the stability. And this one is for the analyze of the bandwidth. Okay, so closed loop bandwidth is normally when this thing goes to, magnitude goes to 0 or -3, normally say -3 dB. And this is our bandwidth. So omega over here is 24. So that's our bandwidth. But you've got a command in MATLAB, just say bandwidth system. It gives you the bandwidth. So you don't have to read from the graph. But I do both ways, just make the visualization easier. So it's about like -3. Not this one. What's the other one? Figure 2. Yeah, -3 dB. If I just run this bandwidth, so omega is our bandwidth. And it's 24.5. So if you look at this figure 2, that's 24.5 exactly, right? When this goes to -3, it's hard to drag it, but you got the idea. That's our bandwidth here. Okay. So once we know the bandwidth, the next thing is sampling frequency. I choose 20 times of the bandwidth. So our omega s is our sampling, not frequency, but this is not hertz, it's in omega, it's 490. So it's 20 times of this 24. And that's our sampling frequency. So sampling time, TS, is 2 pi over omega. So this few steps is from the closed loop bandwidth to get our sampling frequency. That's the first step, how to choose our sampling frequency. So that's done here. We got our sampling frequency is 490 radian per second. Then we choose our anti-aliasing filter. Like we said, this needs to be half of a sampling frequency. So we got omega p, that's the filter frequency. Omega p is equal to 245. So corresponding to this one, this is basically our A is equal to 245. Okay, that's the filter, anti-aliasing filter frequency. And our filter is something like that. Okay, that's in the standard form. So just put omega p in there. So the next 2 steps is to calculate, I'll just run this. So this is the filter. The next one is, this is how much phase loss we got from the filter. So it's negative arctangent omega CP. That's our crossover frequency over the omega p, which is the filter frequency. So if you go back, look at this one, what's the phase loss is this, right? That's this thing. It's this one. But we have MATLAB, so we calculate use MATLAB over here. Omega CP over omega arctangent multiplied with 180 divided by pi. So I just run this. So this gives us like negative 3.7. So 4 degrees phase loss due to this low pass filter. Then the next formula, this looks familiar. Is that? It's negative t over 2 with omega 180 divided by pi. So this is how we calculate the effects of zero order hold. But this time omega is given. You don't have to calculate omega again because that's crossover frequency. We already know that's omega CP, WCP. That's cutoff frequency. We already know. So in here, we calculate the phase loss due to the zero order hold. Is there something wrong? Sorry. So this needs to be TS. I muck around with code last night, so some of the symbols are changed. Where's the TS? We haven't run this. Yeah, that's right. So the zero order hold give us negative like 6 degrees of phase lag. And if we add those two phase loss together, so just this one, just add those two together, you got about negative 10 degrees of phase loss. So remember at the first step when we design our continuous signal system, we have 26 degree of phase margin. So with this digitalization, we lost 10 out of that 26. So which means we're going to be unstable, a little bit unstable, maybe still stable. So this one, I just test if we don't do anything, what's going to happen for the system. See, what I do is I got from the plant, this G and C. G is our plant, C is our controller. I digitalize it. For the plant, I use the zero order hold. For the controller, I use tungsten. Okay, anybody know why do I use zero order hold for the plant?
Excuse me, Professor.
Yeah.
Can I ask one question?
Sure.
Quickly.
Yeah.
Just wondering, can we use randomly any transfer function and any zero, like anti-aliasing filter function for designing controller, or is there any like rule that we have to follow?
Any transfer function. You mean the system model? You mean this model? Yeah,
like in order to start with the controller.
No, you have to have a physical model. You have a story behind it. Like if you have a robot control something, or if you have a motor, you have to have something there. Not like I'm doing this, like ignoring the first step. Like how do you construct this model? You have to do that, or you have to get a model from existing material. If you go to the if you just go here, there's a few models here. If you just go to the modeling, say this is cruise control for a car, right? That's what I use in the example, I think.
Like for example, like if we are using any spring damper function, we construct a transfer function,
yeah.
And then after that, okay, it's like
so
that.
This is that, right? For this case, it's this. This is our model, right? It's this. That's our G, our plan. If you do,
we'll have to start our project from the beginning. How do we achieve that transfer function as well? Is that
yes, that's the modeling part.
Okay.
Or if you have a motor position, you got your transfer function like this one, right? It's a third order system. So you'll get something different. So that's why at the beginning you have to have a story, like what problem do you want to solve? You don't just directly give me random transfer function. Okay, this needs to make sense.
Yeah, thank you.
But the anti-aliasing filter, we always use this one. Use this first order simple structure, right? Just do the simple one. So from, I think difference for you guys is this first one, continuous time control. You have different model, you have different controller. Everybody will have these things are different. But from this going on, you're pretty much doing the same thing. Right? So let's continue. We have a continuous time controller with 26-degree phase margin, and we digitalize it, and we realize we're going to lose 10 degrees. So now let's just see what those 10 degrees mean to us. So I digitalize the plant G with 0 order hold, and digitalize the controller, the PID controller, with a custom. Okay? The reason for 0 order hold is because it's going to be there. It's physically going to be there because it's a plant, a continuous plant. And if you have computer to control it, you have to model that 0 order hold in your system. And then I just do the bow diagram and do the phase margin and also get a step response. So this is just testing the system performance. All right, so you can see if I just digitalize a controller without doing anything, okay, what happened is you can see there's more overshoot. So see, so this zigzag line is the digital controller. That solid line is a blue one is the continuous control. You can see systems are more unstable, right? More oscillation. The reason is because we lost the phase margin. And if we look at the phase margin, because I print this in the box, so it's become 16 degrees, right? There's no magic, right? Because we started with 26 and we estimated going to lose 10 and we actually lost 10. No, sorry. We lost not 26, 20. Sorry, I got it wrong. Phase margin is 20. We start from 26. We lost 6 over here. Our estimation is going to lose 10. So you can see there's a slightly difference here. Okay, so our estimation here, because particularly 0 order hold is a approximation. It's not exact. So we estimate it's going to lose 10 degrees. It's actually lost 7 degrees. It's 26 something gets to 20. WCP is crossover frequency. Sorry, that's not what we're talking about. Okay, so we lost say 7 degrees here. So if we don't do anything, this is going to be the output, and this will be a little bit unstable. And what we want is a controller that performs exactly the same thing, or not say exactly, or have to have a controller performs as stable as the previous one. So we wanted to do something for the discrete controller to make it as stable as the previous one. So we wanted this phase margin to go back to 26. And this is what we do. We design another continuous controller. So this is the original controller. So what we do is, because it's KP, if you muck around a little bit, you know, KP is the reason causing systems getting unstable. If we reduce the KP, system will be slightly slower but more stable. So I keep the KI and KD unchanged. Just make the KP, I'll put a ratio there because I don't know what I'm after. Okay, so I made KB is 0.9, I just make it slightly smaller and see what happened. So the next step is I change the controller, and again I make that controller become a digital controller, and I get the phase margin for that new controller and new system. So I just run this again. What I'm expecting is to get phase margin to be 26 again. So you can see I make the gain is 0.9, so it's become 45. So reduce from 50 to 45, our phase margin goes from 20 to 22. So that seems to go in the right direction. So I make it even smaller. So just try this thing until our phase margin is 26. Now it's 24, so it's looking very close. Let's just say 0.6. This will give us something good, right? So oh, this is getting 28, that's too much. Say 0.7. So because you have a computer, you can afford to like try and error. If you only have a pen and a paper, you can't really do this because every time you have to calculate so many things. So if you have a pen and paper, actually there's a way to directly calculate what kind of gain we should get. But however, we're going to do this with a computer. So anyhow, it doesn't matter. So we can try and error. You got this phase margin become 26. That's become our new controller. So our new controller C here is something like that. So our KP is no longer 50. KI, KD is the same. KP is become 35. And then we look at the system step response. Okay, so if you look at this new one, this yellow one, so you see overshoot is the same as the continuous system. It's a little bit delayed, but it's the same stability. And that's what we wanted to have, because the stability is the most crucial thing for a control system. If it's unstable, then nothing else matters. It's just going to be not usable. Okay, so I wrap up all these again. So the whole idea for this design by emulation is we trying to design a digital controller by considering the problem caused by anti-aliased filter and the zero order hold to compensate these two components by reducing the gain to achieve the same phase margin, same stability. So actually doing that is not very complicated. But when I put that in the slides and explain, it's a lot of things you need to know before you actually be able to understand this. Okay, so this is what we trying to learn from week 10. And also this is what you're going to do for your project. So you have to come up with your own model, your own controller, then follow the steps here to design, to digitalize your controller. So, so after this, you already have your controllers, right? This is your controllers. And next step is, haven't done that. So you have your PID controller. You have your controller C, Z, because I've got this DC, right? Let me have a look. I don't remember that value. Your digital controller is DC. DC. So that's your digital controller, right? With your KP, KI, KD in there. Then you just have to convert that into that's your controller with this is a function of Z. Just the previous one. They can convert this into your UK equal to something something UK minus 1 something something EK, because this is equal to UK over EK. So I didn't do the very last step, but we practiced this a few times. Like this is what we do for the first one, right? After this, you got this UK from EK. This is the same thing, but in this case, the controller is a bit complicated, right? But whatever, this is from a computer point of view, you calculate your current control signal UK from your previous control signal and the error signal, and that's your controller. So that's mission completed. So I haven't got that part, but this is how the whole process for your project should include. All right, does that make things more clear, or you still have questions?
Professor?
Yeah.
Are you going to evaluate us on the basis of complexity of our project, or is it okay if we have just done a simple, like with this project with a simple transfer function and simple design? Because it seems like the more complexity it grows, it's going to be difficult for us to do, because this is what we are doing for the first time. That's why. Not
really, because the complex thing will make it complicated for your first step, but these steps will be almost the same. So I wouldn't evaluate your your kind of marks or give you marks based on how complicated your system is. I will mark your report. Firstly, if you don't make any errors or not. If you make errors, I'll take marks from the errors. Secondly, I will mark based on your understanding the whole steps. You clearly illustrate the process. So that's why I put a 5 minutes question time for everybody, because I wanted to kind of have a face-to-face talk, and you have to explain to me how do you come with this system, and what do you how do you model it, and what controller design, what's the input signal, what's your somebody left me message. Sorry, I didn't read that because I only have one screen. So how do you actually, what's your input and output? How do you control that? What's your goal of your control? What's your phase margin, gain margin? Like, why do you come up with these numbers rather than you just give me a bunch of numbers? Right?
Okay.
I wanted to see your explanation and your understanding. So that's why I got this kind of presentation for this project.
Okay, thank you.
Yeah. Okay, any other questions? This one I will record it. I already recorded. I'll try to put on online, and also I'm available even after week 13. So particularly if you have any questions, send me an email. You can book a time with me, or sometimes I'm available very just at the moment. I will just let you know, and we can start talking, answer your questions.
Is it possible to explain last week tutorial, like question number 4, the zero pole matching method? Question number 1, part in question number 1, number 4.
Oh, I think I just did it, right? Did I?
Okay, I might have missed that, so I'll go through the recording, and if I have problem, I'll come up to you.
Okay, I probably haven't recorded. I don't know when do I start recording. Okay.
Because I joined like 7 minutes after it was started, so I don't.
Oh,
I don't
okay.
know if you...
Did I record that? I can't remember when do I record. I think I did. So if you still don't understand, just ask me a question next time, Monday or Thursday morning. I'll go through that again with you. It's okay.
Okay, fine. All right, I'll do that. Thank you.
All right, I'll stop the recording for now.